reaction force calculation, non-uniformly distributed loading situation. So the first thing you have to do is to calculate that total non-uniform distributed load, the resultant of the non-uniform distributed load. In this case, you are given 10 pound per feet using a triangle. That's the height of the triangle, and the base is 90 feet. So you start highest here, highest loading here, 10 pound per feet, go all the way down to 0 right here. So simply the way you calculate the area under the curve. So that is half times base, which is 90 feet, times the 10 pound per feet. So the total will come 450 pounds. And as you know, that the center of the triangle, that is the acting point of that 450 pound, which is 1/3 from the left side. So that's 450 pound will act from the center. So this is going to be 1/3 of 90. So it's going to be 30 feet from the left side, and the right side would be 2/3 of 90, which is 60 feet from the right side of the triangle. So now we know the resultant of that non-uniformly distributed load and what it is, the location of that load. Next thing we have to do, we have to draw the free body so that we can get the appropriate reaction at point A and B. Assume this is my point A, this is my point B. So I'm going to remove that reaction at point B, which is a rolling contract. So, and then I also, so that will, then I will have to replace that with just simply a vertical reaction at point B. So reaction at B at the Y direction, and I'm going to remove that support at point A too. So that had a knife edge connection, so that will have both. Oops. So that will have both the X and Y component at this point. So we're gonna have both Y reaction RAY, and also at the X component at reaction at point X. Now the second step is to take moments in a way so we can cancel maximum amount of forces. So then likely I'll take moments at point A. So simply you take moments at point A, sum all moment to 0, clockwise, counterclockwise, positive. So if you do that, so for the triangular non-uniformly distributed load, that will cause a clockwise moment. So taking moment with respect to point A, so this solid piece will try to make a rotation like this. So this 450 will do a clockwise moment, which is a negative moment. So 450 times it is 40 feet plus 30 feet away from point A where you are taking that moment, and then that 50 feet will also cause a negative moment. So that's going to be 40 plus 90 plus 10 feet. So that total is 30 feet, that is 20 feet. So that's going to be 10 feet. Now we have that reaction at B, so that will cause a counterclockwise moment. So it's going to try to rotate this way with respect to A. So that's going to be a positive moment RBY, and that is total 40 plus 90 plus 30 feet away from point A. Everything summed to 0. If you solve for BY, the reaction at point B, I calculated that 241 pounds. You can do the similar calculation using find the reaction at point A. You can do simply take moments with respect to B, counterclockwise positive, everything summed to 0. So with respect to B, you have that 50 pound. Now this 50 pound will actually cause a counterclockwise moment with respect to B. So that's positive 50 pounds load times the distance, which is only 20 feet away from point B. Also that 450 will cause counterclockwise moment as well. That is 30 plus 60 feet away minus that reaction at A will cause a clockwise moment. So that's minus RAY component, which is total 30 plus 90 plus 40 feet away from point B, sorry. So that's going to be equal to 0. Now if you solve for the RAY, I got 259 total force reaction at point A. You also have to verify whether you have calculated it correctly or not. So to do the check, the total load, external load, was 450 from the non-uniformly distributed plus the 50 pounds. So that is a 500 pound total load, and then these two reactions will be exact same. So this two corner will carry that 500 pounds. So if you add that 241 259, that should be equal to 500 pounds.